Hello everyone, thanks for checking out this video. This will be the video for the Exam 3 review for Business Calculus, Math 1325. And so I wanted to go over this review with you just to show you how I think you should be thinking about solving these problems, as well as I want to highlight some areas within the notes that you have just to let you know where the information is coming from. And for those of you that are actually taking my course and you're looking at this video, you should know where to get that in eCampus. For those of you that are not in my course, I'm actually going to show the notes and you can just use what I show to be able to help you out to supplement the notes that you should already have. All right, so this first problem here, we're asked to approximate the integral using a left-hand sum using 3 subintervals. And so basically what we're trying to do is this. We want to estimate the area under the curve of the graph of x squared from when x is equal to -2 to when x is equal to 4. So if I draw that, and I'm just going to do that here, for those of you that have to take this test, you don't necessarily have to do what I'm doing right here, but I at least want you to understand where all this is coming from. So let's say this is x equals 2 here, -2 here. This is x equals 4 here. And so what we want is the area on the curve of this function. Pretty much all this area here. And all this area here. So that's what we are trying to estimate. The way that we are trying to estimate the area under the curve is by using areas of rectangles. And so when we're given this information of find a left-hand sum using 3 subintervals, that actually gives us a lot of information. Okay. The first thing that it tells us, if we want to use 3 subintervals, another way of saying that is saying that we want to use 3 rectangles in order to simplify that. In order to estimate that. And pen's writing a little off here, so let's see if I can get it back under control. Yeah, so when we say 3 subintervals here, we really just mean we want to stuff 3 rectangles in between the area here to here to try to estimate it. And of course, this may be an underestimate or overestimate. That part, to do this problem, you're not necessarily worried about that. But you do want to make sure that you choose the right values of x and calculate the right values of y to be able to come up with your length and width for your rectangles. Okay. Now, of course, we know that the number of subintervals that we want is 3, meaning the number of rectangles that we want is 3. And so that's important to us because we know that for each rectangle that we're going to stuff, or try to fit under the curve here, we know that there's going to be associated length and width. And the width of each rectangle is going to be the same as the change in x values. Okay? And so what we know is that the change in the x values is going to be the difference in between the left x value endpoint and right x value endpoint of our closed interval, as well as we're going to divide that by n. So basically we're taking the length from x equals -2 to x equals 4 and going to divide that in 3 different ways. So of course here we know that this is going to be the b, that's going to be the a. So 4 minus -2 and all that divided by 3. That's the same as 6 divided by 3. Let's fix that. And of course, that result is going to end up being just 2. So we know that we're going to have a width of 2 for each rectangle that we have. Okay. Now the length, of course, the length is going to be characterized by f of x sub I, where depending upon what the x value is, that will correspond to how high or what the length of the rectangle is going to be. And so now that we know that we have 3 subintervals or 3 rectangles, and we know that the width of each rectangle is going to be 2 here, then what we can do is we can pretty much know what x values we're going to use. Now we will start off with x sub 0 and go to x sub 1, x sub 2, and x sub 3. Okay. And so x sub 0 is always going to be the leftmost x value endpoint, so that's going to be -2. Since the width in between each rectangle, or when each subinterval starts, is going to be a distance of 2, then I know that if I add 2 to -2, that gives me 0. And of course, if I add 2 to 0, I get 2. And if I add 2 to 2, I get 4. And so these are all the x values that we would choose if we were doing either left-hand Raman sums or right-hand Raman sums, okay? What we want is the leftmost endpoints. So that means we want these 3, okay? If we were doing right-hand sum estimates, then we would use these 3 if we were doing this. But of course, we want this one, so we want x sub 0, x sub 1, and x sub 2. And so basically, what we have now is we know that this is just going, it actually is an abbreviated form of saying the sum from I equals, in this case, since we're doing a left-hand sum, from 0 to n minus 1. And of course, our n here is 3, which is the number of rectangles. So 3 minus 1 is just 2 of f of x sub I times delta x. And of course, this just represents the length or the height of our rectangle, and this just represents the width of our rectangle. And so when we write all this, we know that we're just going to go down the line here. So we first are going to have f of x sub 0 times delta x, and then plus f of x sub 1 times delta x, and then f of x sub 2 times delta x. Okay. And then of course we know that x sub 0 is just -2, so this is just f of -2. X of 1 is just 0, so it'll be f of 0 for here. And for x of 2, we know that x of 2 is just 2, so that'll be f of 2. Now I'm going to go ahead and write this way. And what I mean by that is I'm going to go ahead and factor out the delta x out of all the terms there, because we know that it's the greatest common factor. In other words, the one thing that we see that's alike amongst all of them. So we could rewrite it this way. And so now, in knowing that, to figure out this answer, all we have to do is figure out what f of -2 is, f of 0 is, f of 2 is, and then multiply that answer times delta x. Now, since our actual function that we're looking at is x squared, it's pretty easy. We know that -2 squared is just 4. And we know that 0 squared is 0. And we know that 2 squared is 4. And of course, our delta x, as we calculated earlier, is 2. So when we add all that up, we end up getting 4 plus 4 is 8, and 8 times 2 is 16. And so this would be 16 square units. And so that would be the actual estimate under the curve of that particular function. Now, it's not exact. Again, it is just the estimate. And so before I move on to the next problem, I'm actually going to erase this and give you a drawing of how this would actually look. And you'll see why it's actually, estimated to 16 square units. And I'll also show you if we wanted to find out exactly what it was. Not saying that you would need to do that in this problem, but to just give you a comparison to show you what it exactly was, how we would do that, and then you'll see the difference in between the estimate versus the actual. So I'm going to pause and prepare all that for you and then come back. All right, so I have prepared the drawing for x squared and the area under the curve of x squared that we're using to try to evaluate it using rectangles. And if you look over here to the left, you'll see that I'm using what's called a left-hand sum estimate, okay? And so we know that we're doing a left sum estimate whenever the height of the rectangles are dictated by points on the function. Put another way, do you see how our upper left-hand corner here of each rectangle dictates the height of our rectangle? So that's how you know we are doing a left sum estimate. If we were doing a right sum estimate, then the right upper right hand corner of the rectangles that we would have here would dictate how high the rectangles would be, or put another way, the length of each one. So now you see that for the first area that we have, which is this first rectangle, because remember we have three, this is the first one. So here we see that, of course, it has a width of 2, and this height is going to be 4. Okay. For the second rectangle, if you remember, this is when we evaluated f of 0. And of course, we know f of 0 is just 0. So that's why, even though we have a width of 2, the height of the rectangle is 0, and essentially we're not calculating anything. And then, of course, for the last rectangle here, its area, of course, difference is 2, which is the delta x, or the width, and then the height of that, which is dictated by this point here at x equals 2, ends up being 4. So from a graph perspective, this is what we actually did when we made our calculations earlier. Now notice that this is an underestimate because you have all this area here that is not accounted for, and you got all this area here that is not accounted for. Over in this area, you can see how we did an overestimate for that piece, but overall, we see that there's much more area that's not accounted for here and here than it is there. So that's why this would in turn be an underestimate. In addition to that, if we wanted to calculate the exact area under the curve, the quick way to do it would be to evaluate this definite integral. And of course, we would just take the antiderivative of x squared, which would just be x raised to the 2 plus 1, and divide by 2 plus 1. And we evaluate that from -2 to 4 using the net change theorem. And the net change theorem just basically says if we have some function f of x dx here, then we could figure out the area under the curve from A to B if we evaluate the antiderivative evaluated at B minus the antiderivative evaluated at A. And so that's essentially what we do. Once we take the antiderivative, clean everything up, and then plug in our limits of integration. And then we see that once we're done here, we get 24 square units. And so now you see why 16 square units for the left-hand sum estimate is an underestimate, because of course the exact would be 24 square units. Okay. Now, if we were doing a right sum estimate, Note that that particular value that we would get for our answer here would be over 24 because that would be an overestimate at that point. Okay. So I wanted to make sure that that was clear before we move on to the next example. And so I'll go ahead and clean this up and then we'll work on the second example. All right, so for the next two problems here, for number 2, we want to evaluate the indefinite integral of 3 times e raised to the x minus 6 times square root of x plus 3 times x raised to the negative 1. And for the third problem, we want to evaluate the definite integral of 1 plus x squared from negative 2 to 3. So in example 2, what we're actually doing is we are trying to find the most general antiderivative so that we can find a formula for the area under the curve of this function here. And of course, if we put some limits of integration here, then we'll know exactly from this x value to that x value. But since we don't have any numbers here, this is called an indefinite integral. And when we find the most general antiderivative, we always do a plus c at the end, okay? So the first thing that we want to do is make sure that we rewrite this in a way to where it makes it easy for us to be able to take the antiderivative. So this square root of x, we know that we can write that as x raised to the 1/2. So this term here, we're going to rewrite as 6x raised to the 1/2. And of course, 3 times x raised to the negative 1, we know that x raised to the negative 1 is the same as 1 over x. So what we'll do is rewrite this term as just 3 times 1 over x. And of course, that's important for us because we know that x raised to the 1/2 looks like a type of power function for us. And we can use our rules for power functions for doing the antiderivative for that term. And here we also know that 1 over x is the derivative for natural log of x, or natural log of absolute value of x if you want to be particular. So now that we know that, it's going to be real easy to be able to figure out what the most general antiderivative is. So we'll just come here, and we know that since for this first term here we have a constant of 3, we can ignore that. The antiderivative of e to the x is just e to the x because the derivative of e to the x is e to the x. Okay. For the next term, and that needs to be minus, not plus, we see here that we can ignore the constant again, but now we need to use our power rule for antiderivative. So we do x raised to the 1/2 plus 1, but we're going to write 1 as 2 over 2 and divide that by the same. Then for the last term, we ignore the constant again, and now we know that the antiderivative of 1 over x is just natural log of absolute value of x. And of course, once we're done, since we don't have any limits of integration here, we put the plus c. And so now at this point, all we're doing is cleaning all this up. So of course, we have 3e raised to the x. We know that 1/2 plus 2/2 is going to be 3/2. So here we have x raised to the 3/2 divided by 3/2. And then this will just be plus 3 natural log of absolute value of x plus c. And then for the last part of this, we know that when we divide by 3 over 2, that's the same thing as multiplying by 2 over 3 because we have an understood 1 here, and 1 divided by 3 over 2 is just like saying what is the reciprocal of 3 over 2, and that's 2 over 3. So we'll just finish up writing this. And this will be a minus 2/3 times x raised to the 3 over 2 power. And let's clean that up, make that look a little nicer. Let's just write it all over again, rather. And then we will have 3 times natural log of x plus c. And that is our final answer for that one. For question number 3, we will do the same thing as I did in number 1 whenever I was showing you how to get the exact area under the curve of x squared. This will be similar to that. So we'll start off. Here we know that the antiderivative of 1 is just x, since our variable is x. And we know that the antiderivative of x squared is just going to be x raised to the 2 plus 1 divided by 2 plus 1. So we can just take the definite integral of this. So we'll go ahead and write that out. 1 plus x squared here. Let's get rid of that. X squared dx. And the antiderivative of 1 is just x. And the antiderivative of x squared is just x raised to the 2 plus 1, which is 3, divided by 2 plus 1, which is 3. And we evaluate that from -2 to 3. And so now what we do first is we evaluate our antiderivative at 3. So we're going to do that first. So 3 plus 3 cubed divided by 3. And then minus, do the same thing for -2. So -2 plus -2 raised to 3, all that divided by 3. And so from there, we just compute. So here we know that 3 raised to the 3 is just 27. So we'll just say that that's 27. And of course, 27 divided by 3 is 9. And of course, 9 plus 3 is 12. So that's what goes here. Minus. And so now we know that -2 raised to the power of 3 is a -8. Let me make sure I put this negative here. And so then after that, of course, 27 divided by 3 is 9. And 9 plus 3 is 12. And then here, 2 is the same thing as 6 over 3. Let's make that look a little nicer. And of course, this will be -8 over 3. And of course, from here, this will be 12 minus, and this will be a -14 over 3. And of course, we know that minus and negative is the same thing as addition. And of course, from here, we also know that 12 is the same thing as 36 over 3 plus 14 over 3 will give us 50 over 3. And of course, since we don't have any units, that would just be square units there. And I want to make sure that we all understand, whenever we are evaluating definite integrals, we are trying to find the area under the curve of a function, but we're not literally translating that as area. And so the area under the curve of a function may represent money, or it may represent a distance. And so in that sense, even though it is an area, the context of what the area represents is not necessarily area. So there are instances where we will do problems like this and we have areas that turn out to be negative. But all that means is, and just putting it in the context of money, if we're doing, let's say, some marginal revenue function and we're trying to find the area under the curve of that, what we're really trying to find out is how much revenue we gain from over a period of time. And if we get a negative area as a result, when we do the computations, that just means that we actually lost revenue or lost money, okay? Versus being the net amount of revenue is positive, is actually ends up being negative in those cases. So I wanted to make sure that I put that in there moving forward here, because depending upon what question you have, you may have a negative area for an answer, but in the context of what the problem is, sometimes that will make sense, sometimes it won't, okay? And we'll see throughout this review when that is and when it is not. All right, let's move on to the next problem. All right, so for our next example, we're asked to evaluate this next indefinite integral, where the integrand or the function that we're trying to integrate is x times e raised to the x squared minus 1 dx. And so when we look at this problem, one of the things that we notice here is that we're dealing with the product of two functions where one of the functions is a composition function. And so what that does for us, it sort of gives us a clue as to how to go about doing the integral. Here we're actually going to use the substitution strategy to be able to evaluate this integral. And so what the substitution strategy or substitution rule is for integration, it is just doing the chain rule backwards. So if you remember the chain rule from whenever we were doing the derivative, you'll know that we basically came up with a strategy for taking the derivative of a composition function, meaning that you had a function stuffed within another function. And so what the substitution rule is just undoing that. So here we see that x squared plus 1 is stuffed inside of e to the x here. So we're going to use this as what we're going to substitute. So we'll come here and say, well, let u equal x squared minus 1. And of course, what we want to do now is rewrite everything in terms of u now. And so how we go about doing that is if we take the derivative of x squared minus 1, we're all thinking in our heads right now that, hey, the derivative of x squared is just 2x. And of course, we see an x here. And of course, the dx will just come about whenever we take the derivative. So we have something to work with, but we need to be able to replace x times dx exactly. So we're going to take the derivative of this and we're going to rewrite everything so that we just have x times dx on one side, and on the other side we should have everything in terms of u. So if we take du over dx, meaning the derivative of u with respect to x in Laplace notation, then this is just going to be 2x. And so now we need to rearrange this equation so that we just have x times dx on one side. So to do that, we can multiply both sides of our equation by dx, and if we have that, we end up getting du, which is equal to 2x times dx. And then of course, from here, to get x times dx by itself, we will just divide both sides by 2. And of course here, this would just be x times dx, and du over 2 is the same thing as just 1/2 times du. And so now we have a way to express x times dx in terms of u, and we have a way to express x squared minus 1 in terms of u. And so now when we look at this, we can rewrite this equation, this integral this way. We would have e raised to the u times 1/2 du. And of course, that's much more simple to deal with than what we were dealing with before. So here we can factor out our constant. And now we just have e to the u du inside our integral. And of course, this is easy now because the antiderivative of e to the u is just e to the u. And of course, we append the plus c at the end. And then to finish up, we just replace or put back in what u was. Of course, that's going to be x squared minus 1. And so here our answer is just 1/2 times e raised to the x squared minus 1 plus c. All right, so let's move to the next problem. Okay, so for our next problem, we want to know what is the average value of f of x equals x squared from x minus 1 to x equals 1 to x equals 5. And so when we say the average value, what we're really trying to say is what is going to be the average area under the curve of the function x squared from x equals 1 to x equals 5. And so how we actually find that is this way. So we'll say f average, and we'll call that the average value. That will be 1 divided by b minus a of the integral from a to b of f of x dx. And of course, if this is the case, then we know that our average value for this example is just going to be 1 over 5 minus 1 integral from 1 to 5 x squared dx. Of course, we've already dealt with solving the integral of x squared. And we already know that's x cubed divided by 3, so that kind of makes this simple at this point. So we deal with our fraction. 1 divided by 5 minus 1 is just 1/4. We know that the antiderivative of x squared is just going to be 1/3 times x cubed. We've done that in similar problems here. And we're going to evaluate that antiderivative from x equals 1 to x equals 5. And so we'll go ahead and factor out that 1/3 here and multiply it times 1/4. And that'll give us 1/12. Then, of course, there'll be x cubed left from 1 to 5. And of course, from there, we just substitute in 5 for x, and then minus substitute in 1 for x. And then we just calculate. So 5 cubed is 125. And of course, 1 cubed is 1. So that would just be 124 divided by 12. All right, so here we see that, let me clean up this right quick. We see that both 124 and 12 both have a common factor of 4. So the denominator here, we know 4 goes into 12 3 times. And of course, if we divided 124 by 4, we know 4 goes into 12 3 times, 4 goes into 4 1 time. And of course, this would be the average value, which is about, well, exactly 10 1/3, or 10.33333. This would be the average value of the function f of x equals x squared from 1 to 5. Okay. So now we want to go to question number 6, which is asking us to find the area between the graphs of y equals negative x and y equals x squared minus 2. So what I'm going to do first here is just pause, and I'm going to draw these graphs so that you see what they look like. And then after I do that, then we'll be able to look at this and interpret what we're talking about in terms of area, and we'll know exactly what type of definite integral we need to be able to establish. And so part of the reason why I'm doing this is so that you can have an intuitive understanding as to what our limits of integration is going to be and why that's important. Okay. All right, so now that we have our graph drawn here, let me go ahead and put a y right here right quick. Now we see that we have our function y equals negative x, which looks like this, is in the pink, and we have y equals x squared minus 2, which is our parabola here in the red. And what we want to find is the area between these curves, so we're trying to find out all this area here in the blue. And so if you notice, these two functions intersect each other at two different places here. And so we know that this area that's in the blue here is enclosed by that. So we need to know what these x values are, because those x values are going to be where our limits of integration are going to be. So the x value that's right here, I'll just call it an x of 1, or maybe I should just call it a to go along with our notation here. And this x value here is going to be called b. So the first thing that we'll need to do is actually find out what these x values are by setting these two functions equal to one another. Okay. Now, after we do that, then what we need to do is notice that if we're going to find the area in between two curves, let's say f of x and g of x, we want to do the integral of the absolute value of the difference of these curves. And so all that we're saying here when we do the absolute value is we want a non-negative answer, or in other words, we want the area to be non-negative, so to speak. And another way to interpret that is this: whichever function has the higher y values is the one that goes first, and the one that has the lower y values goes second. So here, when we actually do the integral of this, we're actually going to do the integral of, since y equals negative x is the function that has the higher y values here, then we will do minus x and then minus x squared minus 2. So that's how we're going to have to write that. So we know that whatever this comes out to be, and we'll find out the a and b here in just a second, is going to be minus x minus square root of x minus 2, and all of that with the dx at the end. And so we just need to find out what our a and b are so that we can complete this. Okay, so to find out our a and b, we need to take x squared minus 2 and set that equal to a minus x. And of course, if we add x to both sides, then this will just be x squared plus x minus 2 equals 0. And of course, this is just a simple quadratic equation. So here I suspect that we could factor this. So if we factor, since the signs are plus, minus, then we know one's going to be minus, one's going to be plus, and x times x is x squared. So we know that we're going to have x in both of those places. The factors of 2 are just 1 and 2. And since we want a positive answer here in the middle, we'll put 2 here and 1 there. And if we check out everything here with the outer and the inner, we'll see that we get 2x plus a negative 1x, which will give us a positive 1x, or just positive x. So we know that this is the correct factorization for that. Okay. So I'll go ahead and clean this up right quick. Let's get rid of all this. Because again, we were just checking ourselves there. And so now we just need to figure out what our solutions are. And so just looking at the equation, we can see that our x values are going to be 1 and -2. Because of course, plugging in 1 here will make this whole equation go to 0, and plugging in -2 here will make the whole equation go to 0. So we have x equals 1 and -2. And so we know from this, the -2 will be our a, because that has to be the lower value, and 1 will be our b, because that has to be the higher value. So now we know exactly what our integral is going to be, and we know that to find the, I'll just say find the area here, we're going to do from -2 to 1 of -x minus x squared minus 2, and of course all that times the dx. So now that we understand what we need to do, I'm going to make some room here so that we can finish working on this problem. All right, so now we've made some room, and now we will go ahead and do what we need to do to solve this problem here. So again, we have integral of -2 to 1. And of course, we need to distribute our negative to both terms there. So when we do that, we'll have a -x minus x squared plus 2. And all that will be times dx there. And so from that point, we just do the integral of, or the antiderivative of each term. And let me make sure that we all see that this is just an x. Let me erase. That didn't turn out too well. So that's an x there. Get rid of this 2 here. All right, so in dealing with this, we know that the integral, or the antiderivative of x, is just going to be x squared divided by 2, because of course x is just like x raised to the 1, and we'll just add 1 to the exponent and divide by the same. So here we will have a negative x squared divided by 2. Let's get that 2 looking a little better. Minus, we know, and we've done this several times in this review, the antiderivative of x squared is just x cubed divided by 3. And the antiderivative of any constant is that constant times the variable. And in this case, that is just x. And so we're going to evaluate all that from -2 to 1. And let's just come here and we'll finish this up. So now we need to substitute in 1 first for all of our x values, and then do the same thing with a -2. So we start off with a negative, and then we have a +1. +1 squared, and that is divided by 2, and then minus +1 cubed, all that divided by 3, plus 2, I don't know why this pen is doing this, but 2 with the 1 there. And so now from there, we also plug in -2. So we have a negative, and then separately we have -2 squared divided by 2 minus negative 2 cubed divided by 3, and then plus 2 times a negative 2. All right, so if we go ahead and calculate everything, then of course, for this first part, we have a negative 1/2 minus negative 1/3 plus 2. And then here we have a negative 2 squared, which is 4. And 4 divided by 2 is 2. And since we have the negative there, that would just be a negative 2. Here, negative 2 cubed is a negative 8. And a negative 8 divided by 3 is going to be a negative 8/3. But of course, we have the negative here, so that's going to give us a plus 8/3. And then, of course, here 2 times a negative 2 will give us a negative 4. All right, so let's continue on here. So let's try to move this on, do our equal sign. And then, of course, we'll now change all these into fractions. And of course, if we have a denominator of 2, 3, and 1, the least common denominator is 6. So we know that 1/2 is the same thing as 3/6. 1/3 is the same thing as 2/6. And 2 is the same thing as 12/6. Similar thing here for the second one. We know that negative 2 minus 4 is a negative 6. And of course, we have plus 8/3. Let's make that look a little nicer. And of course, our 6 here, we know that 6 is the same thing as 18/3. So I will go ahead and erase that and replace that with 18/3. And so now negative 3 minus 2 is a negative 5. Negative 5 plus 12 is a positive 7. So we have 7/6 here minus, and over in the next parentheses, we have negative 10 divided by 3. And of course, subtracting negative is the same thing as addition. And to finish this out, of course, we know that least common denominator between 6 and 3 is 6. So we need to multiply numerator and denominator by 2. So this will give us 20/6. And then that will be 27/6. And of course, 6 goes into 27 4 times with the 3 remainder out of 6. And that will give us 4.5. Okay. And so you can choose to leave it as 27/6 square units if you want, or you can translate it into this mixed number. Either way is fine. Of course, we'll just put the square units there. This pen is really acting crazy today. All right, let's move on to our next problem. All right, so now we're at problem number 7 in the review. And so this is a problem that deals with one of the applications of definite integrals, which is calculating probability from a probability density function. And so this problem says we have a life expectancy of a laptop, and that's given by a probability density function below, where X is the number of years since purchase. And so if you notice from our values of X that we are looking at, we don't expect this laptop to last more than 10 years, okay? And the question is, what is the probability that the laptop will last at least 7 years, okay? So if it lasts at least 7 years, then that means it'll last 7 years, or 8 years or 9 years or 10 years or anything in between that. Okay, so that's the first thing that we need to understand. The other thing that we need to understand is what the probability density function actually is and what makes a function be characterized as a probability density function. So for those of you that are on my course, I'm going to go to my notes now so that we can go over that so you can understand why this function is a probability density function. In addition to that, we'll also see what this function looks like in general so that you'll again understand why it's considered to be a probability density function. And we'll also understand why we know our answer should be a positive answer or a non-negative answer, I should say. All right, so I'm going to switch over to the notes now. All right, so for a function to be considered to be a probability density function, first of all, the graph of the function must be above or on the x-axis for all values of x. And so I get that from here because this inequality, when we talk about it from a, let me get my writing thing back here. Yep, so when we talk about this from an algebra perspective, this actually means for what values of x is this function strictly above or on the x-axis, okay? So our graph has to be sitting above or on the x-axis for all the values of x that we're considering, okay? The next thing that has to be true is that the area under the curve of the graph of f of x for all the values that we're considering has to be 1. And so the reason for that is that we're looking at the total area under the curve of a function as being a probability, where probability of 1 is 100%. And so that's one of the reasons why we need it to be 1. Here, the C and the D are the subintervals, so those are the x values that we're trying to figure out the probability in between. And so if we have that, then how we calculate the probability or the area under the curve is simply just doing the definite integral of f of x from C to D. So pretty simple to do, okay? Now, if we looked at the function that we have, we'll find out that if you actually graphed it yourself, this is kind of what the function looks like. So it's actually a parabola that opens down, and of course, this would keep on going this way, and this would kind of keep on going this way if we were still going to draw it. But here what we're saying is that this area that is inside here, the area from x equals 0 to x equals 10 is equal to exactly 1. And so what we are trying to figure out here is this. So we wanted to know what is the probability that it's going to last at least 7 years. So we're trying to figure out from basically 7 on here, what is the area under this curve or this piece of the curve? Because if we can find out this area here, then we can find out what the probability that that laptop will last a total of 7 years or more, okay? Now, just from a common sense perspective, of course, if the area from here to here is going to be equal to 1, or we'll say 100% chance that it lasts 10 years, you see how this area here is much smaller than this area, relatively speaking, okay? And so because of that, we should not get an answer that is above 0.5 for that very reason, okay? And so once we're done, we'll actually calculate that and come back to this just to make sure that everything that we're doing makes sense. So when we talk about a probability density function, we have to know something about the graph of the function, mainly that for the values of x that we're considering, it is strictly above or on the x-axis for all those x values. And we have to know that the area under the curve of that function is exactly 1, okay? And then, of course, based upon the x values of our closed interval here, this is how we calculate that actual area or that probability. All right, so let's go back to the problem. All right, so now that we kind of know what's going on here, we know that to calculate the probability, all we need to do is do the integral from 7 to 10 of f of x dx. Pretty much it. Now, the tricky part is actually integrating this. And so if we do that, we're going to have to break this up into two parts. So, of course, our f of x is -3/500 of x minus 5 squared plus 3/20. And that will be just dx there. And so what we can do here is split this up into two separate integrals. And that will be dx for the first one, and then plus we do the same thing for 3/20 dx. Now, the second integral is relatively easy, and that's because the integral or antiderivative of any constant is just that constant times x. So for the second one here, to figure that out is pretty easy. It's just going to be 3/20 times x, and we evaluate that from 7 to 10. Okay. For this one, however, it's going to be a little different. And since we have x minus 5 stuffed into an x squared function, we're kind of getting the idea here that we may want to use substitution for this part. Okay, so we're going to take this and kind of work on it separately. And so I'm going to go to a separate page to work on this, and then afterwards we'll come back and bring everything together. All right, so to work on this integral here, knowing that we're going to use substitution, the first thing that I'm going to do is I'm going to factor out the constant. And then from there, I'm also going to rewrite what I have here. I really wish this would act right, but we will make do. And so now from here, we're going to use substitution. So we're going to let u equal x minus 5. And so just like how we did in the example, I think it was 2 or 3 earlier in this video, we take the derivative of u with respect to x. And of course, here the derivative of x is just 1. The derivative of -5 is just 0. So here, if we multiply both sides by dx, we just get du is equal to dx. Now, the thing that's different here is that we have limits of integration now. And so we didn't have that in the example before. So what we can do to make sure that we don't have to worry about the limits of integration again by substituting back in what x was, is we can write what these particular x values are in terms of u. So to do that, we can say, what is u of 7? And we'll just plug 7 in here. And when we do that, we get 2. And then we say, what is u of 10? And if we substitute in 10 for x there, we will get 5. So now what this means here is that when we find this out, we're actually going to have -3/500 of the integral of u of 0 to u of 10. Sorry, u of 7 to u of 10. Wrote that incorrectly. And now, instead of writing x minus 5, we just write u and then squared. And of course, du is the same thing as dx, so we just write that as du. course, our u of 7, that is just 2. Our u of 10 here, that is just 5. And so now by doing this, whenever I find out the answer for this part, I do not have to worry about substituting in back x minus 5 for u. So now at this point, we'll just copy down our constant again. And we know that the antiderivative of u raised to the 2, or u squared, is just u cubed divided by 3. And we're going to evaluate that from 2 to 5. And so from here, we will just plug in those values and see what we get. So we'll have 5 cubed divided by 3 minus 2 cubed divided by 3. And of course, from now, we're just doing computation at this point. So, of course, 5 cubed is just 125. And we divide that by 3. 2 cubed is 8, so that'll be 8 divided by 3. So we will go ahead and finish this out now. Okay, so if we have 125 and we subtract 8 from that, we get 117. So that's 117 divided by 3. And we know that 117, because all the digits add up to be 9, which is a multiple of 3. So we know that 117 is divisible by 3. And we'll see that we end up getting 39 when we do that. So all that will be times 39. And of course, from here, we'll just multiply 39 times 3. And of course, that gives us 117 again. And of course, I really could have just, I just saw this, I could have just reduced those 3's to 1, and I would have got the negative 117 over 500. So I'm just going to erase all that and do that, because that's much more easy to do. 117 over 500. Okay. All right, and so that is what that portion of our integral is. Now, I'm going to go back to our problem, and in place of this particular integral here, I'm just going to put this number, and then we'll go ahead and evaluate the other part of the integral and finish out the problem. Okay, so from the work we've done before, we know that for this first integral here, this is just going to be negative 117 divided by 500. And now we're going to evaluate this portion here. And I'll just go ahead and factor out the 3 over 20. And this will just be x on the inside from 7 to 10. And so, of course, this is just 10 minus 7, which that will just be 3. So now from there, of course, we got the negative 117 over 500 plus 9 over 20. All right, so to finish this out, we have 520, and we know that the least common denominator between 520 is just going to be 500. And in particular, 20 times 25 is 500. So we could multiply numerator and denominator by 25 here. And of course, 25 times 9 is going to give us 225. So when we come and finish this out, this will be negative 117 plus 225 All of that divided by 500. Of course, 225 minus 117 just gives us 108. And 108 divided by 500 in decimal form will give us 0.216. Of course, in fraction form, that'll be 27 over 125. But here, if you notice, then what this is actually saying is that we have about a 21.6% chance of the laptop that we were talking about actually lasting at least 7 years. And so that's how we use definite integrals to be able to calculate probability. All right, let's move on to question number 8. Oh yeah, I forgot one thing. Before we go to question number 8, I wanted to go back to this slide here and just demonstrate to you that this is the area that we're talking about here. Of course, we're saying this area represents the 21.6% chance that the laptop will last at least 7 years, okay? So that means from 7 up to 10 years. And remember how we said before, since this was at x equals 7 here, and we knew that half the area would be right at about 5, we knew that this value here had to be less than 0.5. So we knew in the context of this problem, it would be less than a 50% chance that that laptop would last at least 7 years. So I wanted to make sure that you saw that before we moved on to problem number 8. So now let's move on to problem number 8. So for problem number 8, we're asked to calculate the total income over the first 3 years for a continuous income stream with a rate of flow described by this function here, 10,000 divided by t plus 1 quantity squared, where t is in years. And so what we're actually saying here is that, let's say rate of flow of income. If we want to call this revenue, then that would be marginal revenue. And so the area under the curve of a marginal revenue function would actually be the actual revenue. And so here what we're given is the rate in which we are paid this certain income stream. And by the looks of it, it seems like what we are looking at here is a income stream that starts off being a value of $10,000 for the first year, and then after that, it starts to decrease over time. Okay, and so the reason I'm saying that is because of the way that this function looks. So if we look at 10,000 divided by t plus 1 squared, we know that this could also be interpreted this way. Let's make that a t. That'll be t plus 1 quantity squared. And of course, the 1 over t plus 1 squared, the base function for that is 1 over t squared. And that looks like this. So if you're one of my students, I've told you that this is called the band conductor function because it kind of goes like this and goes like that. We know we have a vertical asymptote here at x equals 0. And of course, what we are talking about in particular here is the area under the curve, basically starting all of this area here up to the first 3 years or so, okay? And we see here that if we actually look at this the way that we're supposed to, this function is going to be shifted over 1 unit to the left, and then it will be vertically stretched by a factor of 10,000. So if we draw that, then of course our vertical asymptote now is at x equals -1. And here, right when t is equal to 0, this is going to be 10,000 here. And so our actual function kind of looks like this on this side. And of course, on the other side, it's kind of doing like that. But we don't care about this side because this is only going to be valid from when t is equal to 0 to when t is equal to 3. So we're really only looking at this area under the curve right here. Okay, and so that's what it's asking us. So we start off getting paid $10,000 for the first year, and then we know that that decreases over time. Okay, and so we're just trying to find a way to calculate that. And so what I want to do again is go to the notes so that you can see how we actually deal with calculating the total income for a continuous income stream. And as you guess, we're just going to be doing the integral of the function in between the corresponding values of t that we need. I just want to make sure that you see it for yourself here. All right, so like we discussed earlier, we know that the total income for a continuous income stream, if we have some function f of t, that is the rate of flow of a continuous income stream, meaning how much we get per time period, then the total income produced during that time is just the area under the curve, and we know that we can calculate that by doing the definite integral of the function from the lower time period to the upper time period. Okay, so again, just another application of that. So now we'll go ahead and switch back to our problem to go ahead and work that out. All right, so if we want to find the total income, then we know that we just need to do the integral from first 3 years, so that'll be from 0 to 3 of this 10,000 divided by t plus 1 quantity squared dt. Of course, we'll go ahead and factor out the 10,000, be from 0 to 3, and this would just be 1 over t plus 1 quantity squared dt. And so again, we have a situation here where we have a function t plus 1 stuffed inside of another function 1 over t squared. So that signals to us that we may want to try to use the substitution rule to be able to evaluate this integral. So here we're going to let u in this case be t plus 1. So that means du over dt is just going to be 1 because the derivative of t is just 1 and the derivative of 1 is just 0. And so from that we multiply both sides by dt and we get du is equal to dt. Okay. Now, in addition to that, we also have limits of integration here. So we know that we're going to replace the t plus 1 with u, but we also want to figure out what 0 is and what 3 is in terms of u. So in addition to that, we know that u of 0, if we just plug in 0 into t here, we'll get just 0 plus 1, which is 1. And in addition to that, we'll go ahead and find out what u of 3 is, and of course that would just be 4. Okay. So now that we have everything, our total income is now just going to be integral from u of 0 to u of 3. And of course, this will be, forgot the 10,000 there, so I'll go ahead and move all of this to make some room for the 10,000. So let's say 10,000 there. And then this will be 1 over u squared du, because of course dt is equal to du, and t plus 1 is equal to u. And to finish that, we know that this is basically going from 1 to 4 now, and 1 over u squared could be rewritten as u raised to the negative 2 du. And so now we just need to do the antiderivative of u raised to the negative 2. So finishing all of that now, of course, we'll continue to write our 10,000 here. And this will be u raised to the 2 negative 2 plus 1 over negative 2 plus 1. And that will be evaluated from 1 to 4. And of course, we know that u raised to the negative 2 plus 1 is just u raised to the negative 1 over negative 1. And we know this negative 1 down here is going to make everything here be negative. So I'm just going to factor out the negative out of that. And u raised to the negative 1 is the same thing as 1 over u. And we'll evaluate that from 1 to 4. So now you'll see when we finish up, that we plug in 4 first, that gives us 1/4 minus 1 there. And of course, this is just like 1/4 minus 4/4, because 1 divided by 1 is 1. So we can just go ahead and make that way. And so this is like saying a negative 10,000 times a negative 3/4. And of course, 3 over 4 is like 75%, or 0.75. So our final answer here should just be a positive 7,500. Again, of course, we know this because a negative times a negative ends up being a positive. So we do that. And of course, this is like 0.75. And 75% of 10,000 is 7,500. And so we're saying that the total income received from wherever this comes from, based upon the rate of flow that we have here, is going to be $7,500 or $7,500 over the first 3 years of whatever this investment may be. All right, so let's move on to question number 9. Okay, so for question number 9, we're given a supply and demand curve by it being written algebraically. Our demand curve is going to be d of x, which is 100 minus 0.3x, and our supply curve is going to be 50 plus 0.7x, where x is understood to be the quantity or the demand that we have for a particular product. And so this is a multi-part question here, and the first part of it just asks us to graph the demand curve and the supply curve on the same plane, and from that have us to identify what is going to be the consumer's surplus region and the producer surplus region on our graph. The second part is that after we identify what those regions are, we want to evaluate what the consumer surplus and producer surplus is by using integrals. So what I want to do here is, before we actually do this problem, I want to go back to the notes again so that we can understand what consumer surplus is, what producer surplus is, and what all those areas under the curve or in between curves actually means. And so I'm going to go over the basics of that, go over a similar example to this one, and then after that we'll come back to question number 9, and then we'll see how we actually do this particular problem. All right, so first what we will talk about is consumer surplus. And so the definition of this says, if we have some point on our graph, x bar, p bar for the actual point, where the price demand equation is going to be d of x, the consumer surplus at some price level p bar is going to be, and we just take the integral of the difference in between the demand function and that price level that we're talking about from 0 to x bar. And so as we can see here, we have our demand function, which is going to be this function here. Go ahead and erase that. So this function here. And of course, our price level that we're talking about, P bar, is here. And again, we're talking about this area that is inside there. And what that area actually represents is the total savings to consumers who are willing to pay more than this P bar price here for a product, but are still able to buy the product for P bar. Now, to put this in a real life situation, let's say you're going to buy some shoes. And let's say that those shoes are currently priced at $100, okay? Let's say that you are actually willing to pay up to $125 for those pairs of shoes. So, as a matter of fact, at one time they were probably priced at $125. But let's say it's the holiday season, or it's some special time of the year where they actually start to have sales to try to get people out. And let's say those shoes are discounted to where now they are $100. Since you waited until the shoes were $100 to buy them versus just buying them as soon as you saw them at $125, there's a savings that you as a consumer you experience. And so in this example, we're talking about a $25 savings that you experience. And of course, you're just one person. Now, if there is a certain number of you that wanted that same pair of shoes, let's say around the world, and the demand for that, meaning the number of people that actually wanted that same pair of shoes, and they bought it at the $100 level, is going to be this amount, X bar. And let me move that back here. It's going to be at X bar, which is right here. Can't seem to circle that. Yep, so X bar right there. Then this number of people decided to buy these shoes at this level versus instead of at this level. So the savings that all of you together experience is what's called the consumer surplus. And is represented by the area in between your demand curve here, your demand function, and the horizontal line here that is being represented by this price level, which is in this case the $100. So here's like the $100 here. This is the $125 that you were probably willing to pay. Okay. And so that is kind of how consumer surplus works. Now, if you imagine, we also have a producer surplus as well. And so I'll go ahead and go over that example using a similar scenario here to try to describe what it's saying. So for the producer surplus, it's pretty much the same thing. We're still at some particular point here where this is the number of people that decided to buy a product at a certain level, and this is the price they decided to buy it at. And in this case, S of X is the producer surplus, and this area here is the producer surplus. And what we're talking about here with the S of X function is that is actually the supply curve, okay? And so that would be represented by this here. And of course, the price level would be represented by this here. And so I'm actually going to get rid of this here because this shouldn't be C of S, it should be P of S. And of course, the area that's inside of here is going to be the PS, which is producer surplus. And so in this situation, just think of it being exactly the opposite. So let's say you saw that same pair of shoes that we were talking about before. The producer was willing to actually sell them at $100, and they could still make their profit. However, they said, all right, well, we're going to mark it up to where we're actually going to sell those shoes at $125. And so let's say you go to the store, you see the shoes, you're like, you just got to have them. And a whole bunch of other people, namely X bar amount of people around the world are saying the same thing. Or let's say within a particular market are saying the same thing. So they go buy the shoes at $125 instead of waiting until they're discounted at $100 because they want to make sure that they have them. So in that case, the producer is the one that wins out, or the manufacturer, the business that's selling shoes, they are the one that experiences the surplus now, because each person that bought it for $125, even though the producer still could have sold it at $100 and still made a pretty respectable rate of return, they're experiencing that extra surplus of $25 per person. And so the area under the curve that you see here is just the sum of all the people, X bar, who paid for the shoes at P bar price. And we're just adding that, $25 up, okay? And so in a very simple, crude way, that is what this area under the curve represents. And of course, how we find that out is we end up, this shouldn't be there. It should just be P of S. So we do this by doing the difference, or the area in between the P bar horizontal line and our supply curve S of X. And of course here we see that P bar comes first because the S of X function is beneath it. Okay, so the y coordinates for P bar is going to be higher than the y coordinates for S of X. And of course, this point here, X bar, P bar, is just where the supply curve and the price line there is where they intersect, right here. And of course, here we still are taking the area from 0 to X bar, which is just the number of people who actually bought it at that particular higher price in this case. And so that is what the producer surplus is about. So it's this game of cat and mouse of basically trying to see who is willing to pay more, who is willing to wait out to be able to get the best deal. And so we can actually model this and calculate it by using integration. And so now that we have seen this, I'm going to show you an example of a problem like this so that you can kind of see how the calculations flow. And then after that, we'll go back and do question number 9. All right, so for this example here, and I'll make this a little bigger so that this looks better. So we want to find the consumer surplus at a price level. P bar is 150 for the price demand equation, 400 minus 0.05x. So here, what we're saying here for the consumer surplus, this is going to be the price at which we are going to buy the shoes, even though we could buy it at a higher price. Okay, so of course we calculate this by taking the integral of the difference in between the demand curve and P bar, because since P bar is going to be the price, the lower price, the discounted price, those values, which is the 150, is going to be less than all the corresponding demand values there. And so we know that X bar, P bar is the point where these two functions intersect. And so first, we need to be able to figure out when find out X bar when P is equal to 150. So we basically need to find out when these two functions, d of x and P bar, intersect each other. And so we basically set our demand function here equal to 150, and we solve for x. Of course, when we solve for x here, we see that X bar is 5,000. So this is telling us that 5,000 people within this market, or 5,000 organizations or whatever, actually bought at this particular price here. Okay. And so now when we do the integral, using what we see here, we know that our upper limit of integration is going to be 5,000. And we take the difference in between the demand and the price. So this is the demand function right here minus the actual P bar price. And then of course we just simplify, do our normal integration. And from there you see that we get $625,000. So that means from the total market there, we see that out of the 5,000 people and 150 at that price level, $150, the savings was actually $625,000 that the customers experienced. And of course, if we were to draw that, this is what it would look like. So of course, you see here is our P bar, which is below, our D of X, our demand curve, which is above, and we're trying to find the area that's in between. And of course, since the demand was linear, it was kind of easy to figure this out, even without doing integration. But we know that in question number 9, we have something that is more parabolic, so it won't be as easy to figure out the area. All right, so similarly, we want to find the producer's surplus at a price level of $67 for the price supply equation S of x, which is 10 times 0.1x plus 0.0003x squared. And of course, we see now that the supply is looking more parabolic or quadratic-like. So we really will need to do integration to figure all this out. And again, we notice here that our producer surplus formula is going to be taking the integral from 0 to X bar. And of course, X bar is the amount of people, or the amount of demand that we have that ended up buying whatever it is that we're talking about at this higher price here than what the company really could have sold it at to make a decent profit. And of course, we're subtracting that by the supply function, because those corresponding values for this are going to be lower than or equal to the price here for all the values that we're considering. And so just like how we did with the consumer surplus, we need to figure out when P bar and S of x are intersecting each other. So of course, we set 67 equal to function, and then we figure out what the solution is. And so in this case, since it's quadratic, we can use the quadratic formula for that. And you see, after we do a bunch of calculations and whatnot, we get two answers. One answer is 300. The other one is negative $633.33. Negative 633.33, I should say. It's not in dollars. So we see here that this answer makes no sense because we can't have negative demand. So we pick this answer, which is 300. So we're saying that at this price level of $67, we had a demand of 300 who actually bought it at the higher price. And so now we just go and calculate the producer surplus here. Let me go back. And so we see that once we do that, of course, notice that this is the P bar, and this is your actual supply function here. And notice how I have to go and distribute my negative to all three terms here before I actually start doing the integration. And you don't want to be sloppy with your notation and forget that. So please make sure that you remember to put those parentheses around the supply function and distribute your understood -1 to all terms respectively. And so then after that, of course, we just do the antiderivative of all three terms here and evaluate it doing the net change theorem from 300 to 0. And of course, we see that we end up with $9,900. And so this basically tells us that the producer basically got an extra $9,900 that they didn't have to get because you were willing to pay a price higher than what they could have sold it for to originally get a respectable return. Okay. And so now that we've seen this, we'll now go back to question number 9 and we will work out the problem. All right, so now that we've seen some examples, let us now try to work this problem out. And so as we've seen, we know we have a demand curve and we have a supply curve. And from what we've seen before, the first thing that we need to do is figure out where these two curves are going to intersect each other. We'll need to know that. So let's just go ahead and figure that out right quick. So we have 100 minus 0.3x, and that's going to equal 50 plus 0.7x. So if we solve for x here, we will add 0.3x to both sides, and we will subtract 50 from both sides. Of course, that cancels 0, cancels 0. 100 minus 50 is 50, and 0.7 plus 0.3x is going to be just 1x. So we see that x here is just 50. So that tells us when x is 50, that is where we are going to have both of these functions here intersect. So count this as 10, 20, 30, 40, 50. Then of course somewhere along here they'll intersect. And I'll just go ahead and do this number system out. The rest of these, and same thing here. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Of course, this will be 0 here. All right. And so now what we need to do is find the corresponding value for P, which is going to be our price. And of course, we can plug in 50 into any one of these functions and we'll get the same thing. So if we do it into our demand function, we'll see that the 100 minus 0.3 times 50, that will just be 100, and then of course 0.3 times 50 is just like 30% of 50. That'll give us 15. Of course, that would be 85. Of course, if we do it for the supply curve, we should get the same thing for that. And I just want to calculate it just to make sure that you see that. Let me try to fit this in here. So of course, 0.7 or 70% of 50 is 35. And we drop down to 50 and we see that we get 85 either way. So here at 50 for x, so this is the x bar, and 85 would be about here. If we find the intersection of that, that would be about right there. And of course, that's where both of our functions will be intersecting. Now, I'm going to switch colors here just so that I can draw the demand function and supply function so that we can see how they differ and how all this works now. All right, so first I'm going to do the demand function, and I'll do that in red. And so we know here that since the demand is linear and this is going to be aligned with a negative slope, then our y-intercept is going to be at 100, which is here. And of course, we're going to go through this point here. So we can just kind of draw this line and make it go through this point here. And everything looks good there. All right, and so for the supply curve, we'll do this in pink. And we see that, again, this is linear. And the y-intercept is 50. So we'll come here and we will draw. Let's try that again. Yeah, we're going to draw a line from this point to that point. So go ahead and erase all that and try that again. So we're from here and we will kind of go through there like that. Okay. Now, remember that our P bar is at 85 here. So I want to draw a line to represent that. And so from there, we'll be able to identify where our producer and consumer surplus areas are. All right, so as we said before, 85 is about right in between here. So this will be our constant function P bar. And so now we know that the area in between our demand function and P bar here, and I'll just go ahead and put it there, P bar, that is going to be, our consumer surplus, and what's down here below the P bar and above the supply function is going to be the producer surplus. So I'll go ahead and just label these here. All right, so I've went ahead here and labeled what the consumer surplus area looks like, as well as the producer surplus area, what that looks like. And so this is how we do the first part of this problem here. So now what we want to do is move on down and actually do the calculations for the consumer surplus and the producer's surplus. And so we can use this graph as a guide as to know what function do we need to put before the subtraction sign and what function do we need to put after, okay? So let's go ahead and move on and start doing those calculations. All right, so if we want to start off by doing the consumer surplus, then of course the consumer surplus, we know that this is going to be the integral from 0 here to x bar, and our x bar here is 85 in this case. And just to be sure here, this is x bar p bar, where our x bar is 50 and our p bar is 85. Yeah, so here this is supposed to be x bar. So yeah, that's right. Yeah, that's the wrong number there. There should be 50, which is this number here. So sorry about that. So we go from 0 to x bar. And of course, for the consumer surplus, we see that the actual demand function is the one that is above the p bar function here. So we're going to write the 100 minus 0.3x first. So 100 minus 0.3x. And then we subtract just the p bar, which is 85, from that. Of course, all that dx. For the producer surplus, similar thing. Go from 0 to x bar, which is 50. And of course, now p bar is the high one and s of x is the low one. So we will say 85 minus, and then all in parentheses, we put the 50 plus 0.7x. Of course, all that's on the inside here with dx. And so we've set up our calculations for that. And so now all we need to do is just perform everything. And so I'll make a little bit more room. We'll do these calculations, and then after that, we'll move on to our next problem. All right, so let's do our consumer surplus first. We know from here that if we take the integral of this, of course, since this is just minus 85, everything will pretty much be the same here. So this will just be the integral from 0 to 50 of 100 minus 85, which is going to be 15. So that'll be 15 minus 0.3x. Don't understand why it doesn't curve. Dx. So from there, we'll just do the antiderivative, which will just be 15x plus 0.3 x squared divided by 2, and that will be from 0 to 50. Okay. And of course, for the first one, we'll have 15 times 50. So 15 times 50 plus 0.3, which is like 3 over 10. I'll just do 0.3. And that will be 50 squared divided by 2. Okay. Minus. Now if we evaluate 15x at 0, that is 0. And if we evaluate x squared at 0, that'll give us 0. So for the second one here, we know that we're just going to get 0 for both terms there. So there's no need to write that out. So at this point, we just go ahead and calculate everything. And we'll see that, it looks like I have a wrong sign here. So yeah, I think I put a negative a positive where it's supposed to be a negative. So let me switch that up right quick. So negative goes there and negative goes there. Yeah. That would have been disastrous. So now when we do the calculations for all this, we see that we turn out to have just 375. And so for whatever it is that we're modeling here for the consumer surplus, we see that for the 50 people, organizations, or however the demand is counted, we see that for 50 of them, the total consumer surplus or the savings that the consumer experienced was 375. So now let's do the same thing with the producer surplus. And so for this one, we have to watch it because we need to distribute this understood -1 here to both terms here before we actually start doing our integration. So here this will be from 0 to 50 of 85 minus 50 minus 0.7x. Of course, this will just be from 0 to 50. Let's try that again. 0 to 50, and the difference in between 85 and 50 is 35. So we got 35 minus 0.7x and dx. So now we'll finish everything up. So the antiderivative of 35 is just 35x. The antiderivative of x is just x squared divided by 2. And of course, you see that we ignored the constant there. And we're going to do that from 0 to 50. So of course, this will be 35 times 50 minus 0.7 times 50 squared divided by 2. And that goes whenever we evaluate 50 in. And of course, just like last time, whenever we evaluate the antiderivative at 0, we just get 0. And of course, and once we're done working all of this out, we see that our final answer here will turn out to be 875. And so that is how we work that problem. All right, let's move on. All right, so this example is about the Lorenz curve and the associated Gini coefficient that goes along with that. And what this is really the math of what we call income gaps. And so the Lorenz curve that we have actually helps us to be able to see what our income gaps are in a particular country or population. And so what we're asked to do here, first off, is to be able to interpret what the real life interpretation of x and f of x actually means, okay? And so what I want to do here, again, is to go to the notes to make sure that we see what's going on here so that you get the correct interpretation of what the x and the f of x, or the x and y values for the for the Lorenz curve and what it actually means. And then after that, we'll go and do part B here. All right, so we see here that, let me move this over slightly so that we can look at this a little better. So we see here that we're talking about income distribution, and we know that at least in the U.S., the Bureau of the Census compiles data of distribution of income among families. And so sort of keeps track of how much each family makes, and then of course looks at that as a whole and basically characterizes that mathematically. And so the curve that we get is called a Lorenz curve. And so it puts people, of course, they get this based upon tax brackets. So they'll say, all right, we have this many people that make this much money, and so how many families are like that? And so from that, they can actually build this curve. Now, the variable X represents the cumulative percentage of families at or below the given income level, okay? Or put another way, X represents the percentage up to that amount of families at or below the given income level. Or you could also put it as the bottom, let's say, such and such percentage, okay? The variable Y, or our f of x, represents the cumulative percentage of the total family income received, okay? And so, of course, that's given in percents as well. And so when we have absolute equality here, this means every family has the same income. The Lorenz curve looks like the function y equals x. And of course, that means everyone receives equal amount. So I'm going to go ahead and go on to the next page here, and this is what it actually looks like. So here, our curve of absolute equality here is this, the line y equals x here. And so this is what the actual Lorenz curve is. And you see how it's not as straight as y equals x. And so what this area here is in the middle is the actual income gap, or the gap in income from being ideal from the absolute curve of equality. And so when people talk about the income gap, this is actually what they're talking about, okay? Now, we see, for example, here that if we were to say this point on the Lorenz curve, then that means that the bottom 40% of all families only receive 9% of the total income available for a particular country or population. And similarly, if we're saying a point 0.6, then that means that the bottom 60% only receive about 20% of the total income in a country or population. And so you can see how from that, how majority of the people are only receiving a little bit of the income. That means that the other 40% are receiving the rest of the income, okay? And that's about 74% of the total income is only being received by the upper 40%. All right, so now we're going to see where the Gini index comes into all of this. And so it says if we have absolute inequality of income, that means literally like it's feudal times. We have one family that has all the income and the rest have none. Then the Lorenz curve looks like y equals 0. And so I'll jump back here. That would be like here on the x-axis here. And then of course right here, this would jump up. And of course the one family that has all the income would be right there. Okay. So that's what they mean by that. And so here we know that for our x values, they are going to be in between 0 and 1. And of course those decimal numbers are meaning percentages. Okay. And so the maximum possible area between the Lorenz curve and the line y equals x is 1/2. And I'll jump back there to make sure that you understand that. So here, do you see how we form this right triangle here? And of course, right here is going to be the x value of 1. Here is going to be x value of 0. And of course, since this is y equals x, when x is 1, y is also 1. And when we talk about the area of a right triangle, the area of a right triangle is just 1/2 the base times the height. And of course, if the base and the height are both 1, then you can see why the maximum area of the Lorenz curve could be 1/2. And so what the Gini index does, it is we just multiply whatever this area is by 2. And so instead of looking at it in terms of an area under a right triangle, it just looks at it as a square. And of course, this makes using the numbers here a little bit easier, because now we're not dealing with decimals. We're actually dealing with, well, I shouldn't say decimals, but we're dealing with numbers that will probably be greater than 1 here. So, and of course, the Gini index is 2 times the area between the Lorenz curve, and it can take on values in between 0 and 1 here. So basically, sorry, I didn't mean to say greater than 1. I meant from values in between 0 and 1. So now, instead of dealing with everything from 0 to 0.5, now we're dealing with everything from 0 to 1. And that sort of gives us a better idea of what's going on with some easier numbers. And so that's what the Gini index is all about. It just gives us general idea or a coefficient to be able to compare the income distribution or income gap in between families of a country or population. So now that we've talked about that, of course, what this looks like mathematically is this. So if you remember, we said that for the line of absolute equality would be this line y equals x here. And of course, the Lorenz curve would be whatever this curve is here. And what we're trying to find out is the area in between the line y equals x and whatever the actual Lorenz curve function is. And so that's why we have the difference in between them. Of course, the limits of integration is from 0 to 1. And of course, the 2 times part is just for the Gini index. Okay. And so when we calculate the Gini index, or we can call it the GI here, this is the formula that we use for that. And of course, a measure of 0 indicates absolute equality, meaning that the area in between this curve and this curve is nothing. So it's essentially the line y equals x. And a measure of 1 means absolute inequality, meaning that we're riding along the x-axis here until we get to 1, and then it all goes to one family there. So this is what we're going to be looking at to be able to answer the question that we have. Now, before we get into answering the actual question that we have, I wanted to show you a similar example in the notes that I have, just to kind of give you an idea of how all this works. And that's partly because depending on what version of the test you have, you may have a question like this, or you may have a question like the one that's actually in the review. And so I want to make sure that you get an idea of how to look at all the different types of problems that you may see. So for this one, this says, using data from the U.S. Census Bureau, an economist produced the following Lorenz curves for the distribution of U.S. income in 1962 and in 1972. And so in 1962, we see that this is the Lorenz curve, and in 1972, that is it. And what we want to do is find out the Gini index of income concentration for each Lorenz curve, in other words, for each year. And basically, we want to figure out was the income distribution better or worse from 1962 to 1972. And so we start off by calculating the Gini index for both functions here. So we see how we're doing it for the difference in between x and f of x. Same thing in between the difference of x and g of x. And so I'll scroll down here so that you can see the actual calculations. And so for this first one here, of course, we're just taking an antiderivative of x. And you see how here we distributed the understood -1 to both terms here before we started to take the antiderivative. And we take that, evaluate it from 0 to 1. So we plug in 1 first and then plug in 0. And we see that when we get my answer here for the first one, we get about 0.233. And of course, if we do it again for 1972, again, when we put in our function here for g of x, we have to distribute the negative to both terms there. And then from that point, I factored out a 1/2 here so that my integration here would be a little easier to deal with. And of course, 2 times 1/2 is just 1, and 1 times anything is just that anything. So now I'm just dealing with taking the antiderivative of x minus x squared, which is x squared divided by 2 minus x cubed divided by 3. And I evaluate that from 0 to 1, and plugging in the 1 first, minus plugging in the 0, and we see we get 1/6, or that approximates to 0.167. And so you can see from what we're looking at here, the income gap here was, I guess the area in between there was larger than what it was here, okay? And so now we see from, oops, so, lost that, sorry y'all. Trying to scroll down here to make sure that you can see everything. So here we see that in 1972, the Gini index was lower than in 1962. So this means that the income distribution in the U.S. in 1972 was a little bit more equal than it was in 1962, because of course the gap in between the ideal or the ideal function or the curve of equality and the actual curve here was actually less here because this number is smaller than it was here. And so that's how you would interpret that. All right, so getting back to number 10, we want to interpret what x and f of x are. So if you remember here, x is basically, that did not turn out right. X is going to be the percentage of the bottom X number of people, or X percentage of people who receive Y percentage of income. So again, to just use an example here to make my point. So let's say we have this. So this will mean that the bottom 30% of people are receiving 70% of the income, okay? So X here is the cumulative, or you can say bottom, X percent of people in a, let's say, population, and f of x, which is y, is going to be percentage of total income received. So that's like a simplest way to put it. When you answer this, as long as you put it in your own words and it kind of makes sense in regards to what I was saying here, bottom 30% of people receive 70% of the income. And as long as you put it something like that, and just in general terms, it's fine. All right, so now if we know that our Gini coefficient is 0.4, then we want to know what is n. And of course, n here is what is going to be our exponent there, okay? So to do that, we know that to calculate our Gini index, we know it's going to be 2 times the interval from 0 to 1 of x minus f of x dx. And in this case, we know that the f of x is just going to be x raised to the n. And we know that this is going to be 0.4, so we're going to allow that to equal 0.4 here. So essentially what we're going to have to do here is solve for n. And so to start that off here, of course, just looking at this portion over here, we can divide both sides by 2 to get started here. And if we do that, then that means that we have 0.2 is equal to the integral from 0 to 1 of x minus x sub n x sub n dx. And of course from there, that would just mean 0.2 is equal to, and now we'll do the antiderivative here. This will be x squared divided by 2. And this will be x raised to the n plus 1 divided by n plus 1. And we'll evaluate that from 0 to 1. So I'll make a little bit more room and we'll finish up this problem. All right, and so now, of course, this would mean, and I'll just go to a new line here. So this would be 0.2, which is equal to, we'll plug in 1 first. So that would be just 1 squared, which is 1 divided by 2, minus 1 raised to the n plus 1 over n plus 1. And then minus, and then when we do 0, if we plug in 0 here, we get 0. If we plug in 0 here, 0 raised to just about anything would be 0. So that would just be 0 there. And of course, 1 raised to the n plus 1, that would also just be 1. So all of this would simplify to 0.2 equals 1/2 minus 1 over n plus 1. And of course, we would just need to find out what n is from here. So one thing that we can do here is, just depending on how you want to approach it, I'm going to turn this to 0.5. And we can subtract both sides by 0.5. And if we do that, here, then of course that will cancel. And on the left side here, we would have a negative 0.3. This would be equals negative n divided by n plus 1. And of course, here, since we have negatives on both sides of the equation, if we multiply both sides by negative 1, that will end up giving us positive on both sides. And now we know that 0.3 is the same thing as 3 over 10. This is n plus 1. And now we can just cross multiply to get our answer here. And so this will be 3 times n plus 1, which will be 3n plus 3. And on the other side here, 10 times 1 is just 10. We'll subtract both sides by 3. We'll get 3n equals 7. And of course, divide both sides by 3. And here we know that n will end up being 7 over 3. And so that is what our value would be. And of course, based upon what that looks like, that will also sort of dictate from the line of absolute equality how much it actually dips like this, and thus also affecting how much area is in between both of these curves. All right, so let's move on to our last problem. All right, so for our last problem here, we want to calculate the future value of a continuous income stream with a rate of flow, f of t is equal to 100 times e raised to the 0.2t. After 10 years, if interest is compounded continuously at an annual rate of 2%. And so that last part is just basically describing what's happening here with this function. The way that this looks, 100 times e raised to the 0.2t just basically looks like an exponentially increasing function. It kind of goes like this, and of course the rate at which it's increasing is going to be at a rate of 2%. And so we're basically just trying to find the area under the curve of this particular function here for the first 10 years. So again, I'm going to go to the notes so that we can see what the formula for future value is, future value of a continuous income stream, so that you will know what formula to look for on your formula sheets so that you can use that to calculate this. So for the future value of a continuous income stream, we know that the continuously compounded interest formula is just this PERT formula, P times E raised to the RT. So that's what I was talking about before. If f of t basically describes the rate in which we're receiving some income here, and we're assuming it to be continuous from a time 0 to t, and then for the problem that we're working on, this big T here is going to be 10. And if the income is continuously invested at some rate R, which we know it's at 2% for our problem here. So for what we're working on, this is 10, and here this is 2% or 0.02. Then the future value is described by this formula here. And so you can either look at it this way, or you can look at it this way. And the reason why they're rewritten here is because here we're using our exponential rules. If we were to distribute the R to both terms there, then we would have e raised to the R big T minus R little t. And we know from our exponential rules that whenever we have a raised to difference of exponents here, that's the same as saying a raised to the x, here, divided by a raised to the y. Or you could put it in multiplication terms like this, okay, where we know that a raised to the y is the same as a raised to the negative y is the same as 1 over a raised to the positive y. And so what's happening here is that this rule is being applied to rewrite this as e raised to the R big T times e raised to the minus R little t. And of course, big T is a number that you know, R is a number that you know, and E is an irrational number that you know. So this is just a constant. And so that's why the e raised to the R big T is being factored out of the integral, because it's literally just a number. And all you have to do now is work with whatever this particular integrand is. And of course, based upon what the function is, you're multiplying that times this exponentially decreasing function here. And from that, you just do what you need to do to be able to take the integral. So that's why this function looks this way, and that's why this formula looks this way. And depending upon what works best for you, you could write it in this first form or the second form. So now we'll go back to our example and then rewrite this formula and work the problem out. All right, so we know here that future value of income is just going to be 0 to big T of f of t times e raised to the r big T minus little t dt, like that. And of course, from here we know that we can rewrite this as e raised to the r big T integral from 0 to big T of f of t times e raised to the negative r little t dt. And so what we want to do now is just go ahead and plug in what we know. Well, we know our r here is 2%, which is going to be 0.02. That didn't come out too hot, but hopefully you get what I'm trying to say. So r is equal to 0.02, and of course big T is equal to 10, so that would be 0.02 times 10, integral from 0 to 10 of 100e raised to the negative 0.02 t times e. Don't need the negative there because f of t is just 100 times e raised to the 0.02 t. And then we need to multiply that times e raised to the negative, let's get this writing, negative 0.02 t here. Right, and we need to make sure that all of this dt. And so now if you notice here, we have e raised to the positive 0.2 t times e raised to the negative 0.02 t. And so if we combine those exponents together, we're going to see that that's going to go to 0 here. And so I'll write that in just a second. We also see that 0.02 times 10 is just going to be 0.2. So we'll go ahead and take care of that. And here this will just be 100 times e raised to the 0.02 t minus 0.02 t dt. And of course, that just cancels to 0. And e raised to the 0 is just 1. So this turns out to simplify itself rather well here. It's from 0 to 10, and this just ends up just being 100 dt. And so now when we take the integral of this, of course the integral or the antiderivative of any constant is just that constant times x. So we have this 100 times x, and that goes from 0 to 10. And then to finish up, all we do is substitute in 10 for x, and then substitute in 0. And of course here, that goes to 0. 100 times 10 is 1,000. And of course, our final answer here is just 1,000 times e raised to the 0.2. Of course, to finish this out, if we were going to find out what that was going to be in decimal, that would be 1,221.41 roughly. And we'll just say that this is in dollars. So put dollars here. So for whatever it is that we're starting off with $100, and our $100 is growing at a compounded continuously rate of 2% a year. Then in 10 years, that $100 will turn into a little over $1,221. All right, so again, I know that these reviews are rather long, but I want to make sure that I do a very detailed job of trying to get you to understand what I think you should know for the exam and some of the things that you need to consider. I'll also try to throw in some notes in there just to make sure that you are looking at some of the things that you need to be able to be successful on the exams. So I hope this helps, and good luck to you. Take care.